seems to be fitting all right. I'll see if I can't fit another one. This one's kind of small. I'll put this one in there too.
Put your goggles down.
All right. Yeah, the goggles are for protecting your forehead. Put goggles on, please. That seems to be working. Let me put this green one in here too.
Got my own balloon. You can't take it.
So, yeah. Yeah, that's working. All right. How about let's get this blue one over here.
Oh, I know what's happening.
So, anybody have an idea of how many balloons I can fit in here?
Oh, infinity.
Infinity, really? No, it's not even close to infinity, but I could probably fit about 100 in here if I really wanted to. And it's definitely not the highest number in the world. There is no highest number. You can always come up with a number higher than the other number. All right, I'm not going to dump it out because then we waste all the liquid nitrogen, but I will show you why I can fit so many balloons in here.
It melts. Because it's milk.
Now don't touch these, okay?
Toad.
That looks like the balloons they got in the store.
Back up. Edie, blow back up. That's cool.
Pretty neat, right?
Put this one in.
Oh yeah, it's just trapped in there. So anybody have an idea why the balloons did that? Yes.
Hey. Hey, guys.
Where would the gas enter and leave the balloon?
The hole.
The hole? There's no hole in these balloons.
Where you blow it up.
Nope, that's tied shut. No gas is entering or leaving the balloons. What else could it be? Anyone? The heat? What about the heat? Keep moving? You're getting warmer, but what exactly? Yes?
It's so cold that it makes it smaller.
That's right. It's so cold that it causes all of the molecules of the gas to contract. When things get colder, they get smaller, right? So it got so cold that the gas molecules inside contracted and there were no longer enough pressure to keep the balloon inflated. But once it started warming up, that got the gas particles excited again. They started spreading out, and that caused it to expand again. All right. Now, we've had another couple of things in here this whole time. Let's see if this has had enough time to... Let me give that a little bit more time to cook in there, and we'll try this. All right, so liquid nitrogen is very, very cold, and if it comes into contact with anything near room temperature, it boils away instantly. So watch this. Completely gone, right? Now I'm going to pour a little more on the floor, and this time I want you guys to keep an eye out for lots of little tiny water droplets, well, not water droplets, but little tiny droplets scooting around on the floor, okay? Please don't touch them, but if they come in contact with your shoes, you're fine.
My shoes.
Do you see the little ones? Little droplets scooting around on the floor? Did you see them? Okay, one more time. Do you see them? Can you see them scooting around? All right. So that is an example of something we call, well, guys, attention, called the Leidenfrost effect. The Leidenfrost effect is when something that is a liquid instantly boils upon contact with a surface. It'll create a little cushion of air between the droplet and the surface it's coming into contact with, and that creates it almost like a hovercraft, and the little droplet just hovers around on that little cushion of air. You've probably seen it before if you've ever made pancakes on like a really hot griddle, and then you pour water on the griddle, and you keep the water droplets scooting around. That's the same principle. That's the Leidenfrost effect. All right, next up, I'm going to pull this out. We've had this in here cooking this whole time. Hopefully it is cool enough. We've got a tennis ball. Now, normally tennis balls are pretty bouncy, right? But I'm going to drop this really cold tennis ball on the ground. Do not touch this tennis ball. If it rolls towards you, leave it alone. All right? So here we go. That's not very bouncy. Let me try that again. Let's see. Now, kind of sounds more like a billiard ball than a tennis ball, huh?
Like a rock.
All right. Now let's try this. I'm going to take this tennis ball. I'm going to hit it with a hammer. Everybody ready? All right, again, if this tennis ball comes near you, do not touch it. I'm going to try and make sure it doesn't move.
Cover up my face.
Oh, yeah. Cracked it. Let's try one more good hit. That was not a solid hit. Yeah. As you can see, rather than squishing, this tennis ball is fractured. It's cracked. You can feel it. You can hear it. It's all crunchy. You hear that? No! No, do not touch this. It is cold enough to hurt you. All right. So, what happened there? Does anybody know what property makes bouncy things bouncy? What? Well, gravity pulls it down, but that's not what makes it bounce. Yes. It's a property of the object. Yes. Why is rubber bouncy? It's another bouncy thing, but why is rubber bouncy? Oh, maybe it does now. Yeah. Yes. Elasticity. Very good. It has a property called elasticity. That's really simply how much it wants to stay in its normal shape. Okay? So, this tennis ball's normal shape is round. When you drop it on the ground, it squishes against the ground. It deforms a little bit. You know, Newton's law, equal and opposite force. So when it hits the ground's pushing back on it, and it's squishing it. It's deforming it. But it doesn't want to stay deformed. It wants to go back to its round shape. So the molecules push back out again. And that forces it back up into the air. Then gravity pulls it back down. It squishes and deforms. The molecules say, no, 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 going back to round, pushes out, and once again it goes back up the air until it runs out of energy. All right? And that's why bouncy things are bouncy. It's about elasticity. In the opposite way, you can see that also with a rubber band. It wants to stay in its small, rounded shape. If you stretch it, it's deformed. And as soon as you release that pressure, that energy, it goes back to its smaller shape, right? Because it is elastic. All right. Now, besides just reducing elasticity, oh man, wow, this onion shattered inside here. We put an onion in here so you can see what happens to organic matter that gets really, really, really cold. I don't even need to hit this thing. It's shattered anyway. Let's see if I can get all of it out here. But yeah, now I said earlier that our bodies are comprised primarily of water. About 80% of our bodies are water. And water is fairly special, not completely unique, but fairly special in chemistry in that it's one of the few materials that when it freezes, it actually expands. And that's because of its electromagnetic properties, but we won't get into that right now. But unlike most things, water expands when it goes into its solid form, it's ice. Since our cells are primarily made of water, when you get cells really, really cold, the water inside the cell expands and breaks apart the cells. It shatters them, it tears them up from the inside. So that's why this onion is now breaking into little tiny chunks, because we have actually destroyed its cells from the inside out. That's why cryonics, the process of trying to preserve something by freezing it, really doesn't work so well. Because, yeah, you can freeze it, but it's destroying it in the process. So, if you ever thought about having your brain frozen so they could revive you someday, probably not going to happen, just so you know. I do have a little chunk here I could probably hit with this hammer here. Let me put it inside a bag so I don't get chunks of onion flying everywhere. And I'll shatter this onion for you.
Thank you.
Bro, come on. There we go. It does sound like glass. Very good. So I'm going to put it inside this plastic bag and I'm going to hit it with a hammer. You guys ready?
Yeah.
All right. Here we go. 1, 2, 3. And it sounded like glass breaking, right? It sounded like almost like a light bulb being smashed. Now we have lots of little tiny chunks of onion. Just like that, just like if you had broken glass. All right, so the final thing I'm going to show you guys. We have to refill our liquid nitrogen after this. And pour the rest of the liquid nitrogen here into our cooler. And we have some very hot soapy water. Oh, warm.
Dirty.
It's hot? Okay. And what I'm going to do is take this soapy hot water and pour it into the liquid nitrogen. You guys should stand back. Get on the other side of the table, please. Keep moving. Keep moving. And yeah, goggles on the face, please. All right, I'm going to button up my red hoodie a little bit. All right, so what's going to happen when I pour this water in here? Actually, anybody want to make a hypothesis of what's going to happen? Yes.
They can see.
A lot of smoke? Steam. So there's going to be a lot of steam. Okay, yes? Guys, quiet please.
The white thing right there is going to break. That's why you put it inside there so these things go in there.
Well, I'm hoping it doesn't blow up, but sometimes it does. So, okay, we've got a couple hypotheses. Let's see what happens. You guys ready?
Yeah.
All right. In 3, 2, 1.
Oh!
So, did you expect that? No. No. We got an explosion.
What happens if you breathe this?
Nothing. That white vapor is actually water vapor in the air that's condensing because of how cold liquid nitrogen is. Guys, are you really crawling under the table?
I told you.
All right. But what just happened is I put the really hot soapy water into the liquid nitrogen, and that caused the liquid nitrogen to flash boil really, really fast because of how hot that water was. And when it boiled, it expanded. Most things expand when they change states, all right? So it went from a liquid into a gas, and it expanded to 7 times its volume. So it takes up 7 times as much space. So suddenly we have a lot of nitrogen gas coming out. But there's soap in there, and soap tends to trap gas and make bubbles. So we got a whole lot of nitrogen gas expanding and turning into bubbles really, really quickly, and all of it was trying to escape through the very tiny opening there in the top of the cooler, and so it went boom in a big explosion of bubbles. And now, you guys can look at these, do not touch, but look at the flash frozen bubbles. Back up, please. There you go.
That looks like a plastic bag.
It does kind of. So these bubbles were frozen before they had a chance to pop. So they flash froze as they were being formed. Pretty nifty looking, huh? If you guys are in the front, let some people in the back get a little closer and take a look. So everyone can get a good look at the frozen bubbles. There we go. Everyone get a chance to look at them? Pretty nifty, I think. All right. So there you have it, folks. That is liquid nitrogen. Very, very, very cool. Now, does anybody have any questions? Because I think we're getting real close to lunch. We are. We have 4 minutes. All right. So if everyone would please take off your goggles, just put them right here on the table, and we'll take care of getting them back where they need to go. And then, Rachel? All right, Rachel. Miss Rachel here will lead you to the cafeteria. You guys